Hello everyone. Today a little review of what we know about ideal springs. So if we were to graph the force exerted by a spring versus its elongation and or compression, we know that we would get a linear graph that would be in the second and fourth quadrants. Right? This is if we're treating these as vectors. So since it's a linear graph which goes through 0, 0, right, that's showing that the force and the elongation are proportional, but because we're in the second and fourth quadrant, they're also opposites of one another. Why are they opposites? Well, if you stretch a spring, it pulls back in. If you compress a spring, it pushes back out. So the force exerted by a spring and its elongation or compression always act in opposite directions. That's why we've got that extra little negative in there. Of course, we then defined the slope of a force exerted by a spring versus its elongation graph as the spring constant, denoted by a lowercase k in an equation. Plug that in. And that's a measure of how strong or the elasticity of the spring. Springs with greater spring constants are stronger springs. They exert more force for the same amount of stretch or compression. Plug that in, and we get that the force exerted by a spring is negative kx. Right? Negative spring constant times the elongation or compression. This, of course, is named after Sir Robert Hooke and is known as Hooke's law. And it is true for ideal springs, sometimes associated so much with Hooke that they are called Hookean springs, usually cylindrical springs like the ones we've been using in lab. Right? So remember that this is a restoring force, and it's the kind of force which gives rise to simple harmonic motion. So that being said, I want to do a little lab now about the period of this mass on a spring. Remember, period is the time for one complete vibration. That would be like, say, from the far right to the left, back to the right, from the top to the bottom to the top, right? One complete motion. Well, what things do you think we could change about this situation that might affect the period, that might change it? Well, maybe we could change the object, and by that I mean its mass. Perhaps we could change the amplitude that it's vibrating with. And one other thing, maybe we could change the spring, or functionally, change the spring constant. Right? We could do that by using a different spring, and maybe it's longer or shorter or uses a different kind of wire. Right? All those things that would affect the spring constant. Well, this is a lot of variables to test, right? So we could do 3 labs and test the effect of mass, amplitude, and spring constant on period, but I want to help you with one of these. So I got a little video I want to show you that's from Pivot Interactives. Here are a bunch of masses, all right, with identical spring constants, or identical springs in mass, okay? The difference here is that their amplitudes are different. So same spring constant in all of these springs, right? Same mass hanging. They're all attached down here, and they're about to cut the little cords. And he's got it synced up, so they're going to cut them at the same time, right? So watch what happens. Now look at the period, the time to go up and down once. And notice that it's all the same, right? Takes the same amount of time for this one to go up and down as it does this one over here, even though the amplitudes are very different. Right? So that little movie is a great demonstration of the fact that amplitude doesn't affect the period of a mass on a spring. You might be saying, well, why is that? Well, because the amplitude is going to change 2 things. Yeah, if it's got a bigger amplitude, it's got to cover more distance to complete a period, but with a bigger amplitude, there's more forces involved, and more force means a greater acceleration. And so it can basically eat up the extra distance it has to cover due to the greater acceleration. So that means we can cut amplitude out of the list, which is going to, cut by 1/3 how much we have to do in the lab. And so that leaves us with a purpose to create graphical and mathematical representations of the relationship between the period, the mass, and the spring constant of the mass on the end of a spring. Right? And we're going to be able to vary all these things. Right? We can change the mass on the end of the spring, thereby making that an independent variable. We can swap out the springs so that we have springs of different spring constants. And then we can measure the period. Now, the technique we're going to use to measure the period is to count 10 periods and then divide by 10 to get an average. So rather than trying to find one period, which sometimes can be a little fast and could have some reaction time error in there, okay, we're going to, start timing, count 10 times, 10 periods, stop timing, divide by 10, right? We'll take the average period. And that should get us a little bit better of a value so that we don't have to do a bunch of trials, right? Because we're just going to take 10 and divide by 10. All right, now this is going to take a couple of different labs. Right, so you're going to have to do a lab where you vary the spring constant and measure the period and keep the mass constant. And then a lab where you vary the mass and keep the spring constant and measure the period. Right, so 2 labs here that we're going to have to do, changing one variable at a time. And then in the post lab, I'll show you how we will put them together into one big equation that will allow us to calculate the period of a mass on a spring.